things, so it's a big old puzzle, right? Identifying people, John and Jane Doe. Hear that on the programs, Doe, Jane Doe. That's what we use. We don't know. That's fun. Catch the bad guy or the perp. Another good word. Pocket. Challenging, difficult, messy, gross, nasty, time. All of those. Okay. So it's all of those things for us scientists and for law enforcement. We all work together to solve a crime. So it's a marriage. It's a marriage of science and law. Okay. It's an intimate connection between science and forensics. So here's an example here of the Night Stalker. Anyone remember that case? Yeah, back in the 80s, 1 year. 1 year he murdered over 12 people, right? But many years later, in 2009, when he was on death row, the advances in DNA technology that we had, we were able to go back, take some of that evidence and re-examine it, and he was linked to yet another murder. So we've come a long way, especially with DNA and fingerprinting, especially, which is an individualized. We were able to connect Richard Ramirez to another case that had been previously considered a cold. And we use the forensic science technique to solve crime. Well, here's where we use chemistry. I love the chemistry one because I love to make all the different colors and stuff. So lots and lots of times at a crime scene, if there's drugs stuff involved, there'll be white powders or white pills or maybe even blue pills and different things, pink, things like that. But they all come down to different kinds of chemicals, right? Some of them are medications that are good for you. Some of them are drugs that are abused. So when we find a bunch of white powder at a crime scene, we have to try to figure out, is it heroin, cocaine, is it oxycodone, is it methamphetamine, or is it just call it denture powder? I mean, it could be, right? Baby powder, all kinds of things. Could be many things, benign things, very dangerous things as well. So what we do is if it's not already ground up powder, grind it up powder, and we put it in these little dishes called a spot plate, and we add different. We know from experience, from past, that if you mix a white powder or a tablet with a certain chemical, you'll get a color. It'll tell us, oh, that's heroin, that's cocaine. That's the first part. Then we have to do more tests to make sure that it's not a cross reaction. That's kind of an initial, what is this? Police departments now today have little kits. Do you have any police officers? They have little kits that they take actually right there when they stop somebody. If they suspect drugs or whatever, they see it, they can test it right there and go. So then we do presumptive tests for blood. Okay, we take this chemical called phenolphthalein, colorless, and we put it on what we find at a crime scene that looks like blood. It could be ketchup. It could be all kinds of things. You wouldn't think so, but many reddish liquid type things look like blood when they dry, especially if they've been there for a while. But if we happen to have blood, real blood, the heme, a component of the blood, plus that chemical and a little bit of hydrogen peroxide will give us this bright big color. So now we know, okay, this red dot on the floor, at least we know that it's blood. But we still don't know at that point if it's human blood or some other animal. So we have to go on and do more tests. But it gives us a good indication if we're selecting the right. So like I said before, you have to confirm, is it human, animal. So it's kind of like a color game. Like, it's a lot of fun. And then we use biology. Watson and Crick in 1953, they described the DNA model, and that opened a whole new world. Now all of a sudden they realized, oh my gosh, everybody in the world has DNA. What a great tool for examining crime scenes like that. Here's a couple of my students doing some DNA analysis, turning graduate way back. So basically, I don't know if anyone's ever thought about this, but one human being to the next, all of us, over 99.9% of our DNA is all the same. we're all the same. That's why we all basically have head, two eyes, a nose, all of these things. But is that little tiny spot that's different? That's what we're looking for, that degree of variation. We use this thing called RFLP, and very long word, restricted fragment length polymorphism. You don't need to know that. But what it does is it takes advantage of that different, it recognizes that different people's DNA, and it chops that piece out. Then we take that piece and we do what we call PAR, polymerase chain reaction, and then we make a lot of copies. Now we have a lot of DNA that all the same. It doesn't change it, and it's from a variable part with DNA we're looking for, and then we can do a bunch of big advanced science. And in the 1600s, microscope was introduced by Lewin van der Hoek. Pretty cool tools. All of a sudden, you go from invisible to visible, right? Things you couldn't see before, now they're right there. You can see them. Maybe long ago, obviously, than I am. Teaching one of the students on a comparison microscope. Comparison microscope take a bullet over here and a bullet over here, one from the crime, one from the suspect gun, and you can look at them at the same time, all the magnification of it side by side, see if they're a match. That's a very important tool for us. Microscope was just an amazing invention. Does anybody know what this bottom right thing is under the microscope? What is it? Pollen? No, it's marijuana. So this is cannabis. Nobody knew. Come on, you just didn't want to say. You just didn't want to say. That's cannabis, and interestingly, of course, if anybody's ever seen it, it can look a lot like oregano, parsley, all these different things when it's dry. Okay, when it's all dried up, plant, but when it's dried up. But when you look at it under the microscope, it's quite different. Cannabis has what we call beer claws. There's little ones here, and for some reason, I think the screen is just so beautiful and bright. My pointer doesn't work very well. But right at the end, it looks fuzzy. These little hooks. So other kinds of herbs do not have that. The marijuana has. Now we know. Okay, we probably got marijuana. And we use physics. We use physics, which is the nature and properties of energy and matter, how things move, right? So to determine mostly possible positions, here's the Kennedy case, right here, John F. Kennedy assassination, 1953, and this right here, 63, I'm sorry. This here is a picture of the skull. You'll see it in another second. And where drawing was made to show where the entrance and exit, because why would that be important? Then we know, where did that shot come from behind? Did it come from in front? Come from the side, right, or the left? Very, very important information. Unless, of course, you have two famous experts, Dr. Angel and Dr. Baden, completely disagree as to what is the bottom picture on the left. Dr. Baden said the exit wound was where the blue dot is, and Dr. Angel said the exit wound was where the green dot is. So based on their figuring out projection and all that, they came up with that. Didn't help. Part of the problem was a lot of the things that they worked on by the time they were brought in. A lot of the drawings and things that they worked on were based on recollection from nurses, people like that who were at the scene, and they were kind of didn't all match what they remember. Just like if something happened in this room today, you could interview everybody here and all have a slightly different way of saying what happened, right, or what you saw. So they disagreed. That was very unhelpful. So in that case, when John F. Kennedy was assassinated, they should have brought in a forensic pathologist. They did. They had government pathologists did this job, and it was not from the beginning. So those people, the people who are experts, get right in the initial. Then we use photography. Photography is awesome. Back in the day, when the detectives were walking the beat and the cops, they would take a picture of the crime scene and then walk around the neighborhood with the instant camera and walk around the neighborhood. Anybody know this person? Things like that. Now we have digital. We have color, black and white, slide, maze. What it does is it freezes something in time so that afterwards, if that thing or that collected as evidence or person moved or changed, we have how it looked when the event occurred, or at least as close as possible when the event occurred. The top left is Annie Lee, and she was a graduate student, and I talked a little bit about her the other day from Yale University, and she was doing a research project for her doctorate like Tuesday, and she was getting married on Saturday. And she had a person that worked with her, the Raymond Clark. He was in charge of the animals. Didn't like treat the mice, rats, stuff. So he strangled and left her in the building at Yale University. The last picture we have of her is her with her supplies for her experiments going into a building at Yale. So we have no pictures of her coming out, and all of the buildings there happen to have cameras, so that was a great thing. So we knew from that, going in, no going out. She's missing. We knew she was in that building. It still took a couple of days to find her. It was based on that, so it didn't waste time out there in the general public looking everywhere.